couple more things I neglected to mention at the end of the last video clip. So this is Spacetime Diagrams Revisited Part 1B. And that is, here's our diagram again. And we have a light beam. Say we're measuring, first of all, x in light years. T then is assumed to be in years here. And we can confirm that because we see that this world line here, v equals c. And that's at a slope of 1, and therefore c is 1 light year per year, or 1 whatever light seconds per second, if the units happen to be that. And then I've drawn a couple other green lines in here. As you can see, we've got v equals 0.5 c, v equals essentially 1/3 c. And over here, here's a light beam traveling in the negative x direction. Again, this is all happening in the x direction. It's not going up at some angle. That's just our time axis there. So this is a light beam traveling at negative c, velocity negative c. In other words, going in the negative x direction at velocity c. And similarly here for the 0.33 c, I could have a, let's get the green one here, have one like that. That would be negative 0.33 c. In other words, moving in the negative x direction as time goes along. And v equals negative 0.5 c would be about something like that. Another thing to note here before we get to this red line is that when we have diagrams like this, and we're talking about the fact that nothing can go faster than the speed of light, and that'll actually be a topic for later on this week. We'll explore that a little bit more, what might happen if things can go faster than the speed of light. What that means is we're never going to have any world lines that are sloped less than the v equals c line here. Because if I have a line here, with going off this way, that means that object is traveling faster than the speed of light. It's going a certain distance x within a certain time t faster than a light beam can go. And so all the lines we see are going to be in this region here between v equals c going that way and v equals negative c going that way. And so you'll see them typically angled like that, like 0.5 c, 0.33 c. Note that quote-unquote normal everyday velocities would essentially be vertical lines. If this is 1 light year, right, that's billions of kilometers, and therefore it would take, if you think about it, that for a year even, if t was a year here, 2 years, 3 years, you'd just go slightly over on the x-axis. Okay, so we're talking about astronomical speeds here, speeds going at appreciable fractions of the speed of light in our examples. Okay, then finally, what about this red line? Well, think about this a minute. If I said, okay, this is the world line of something, describe to me what it's doing. Okay, we say, well, at t equals 0 here, it's at x equals 3, so the 3 light year mark. And then as time goes on, it's clearly moving to the left because the line is sloped in that direction. And so here it's at t equals 0, it's at x equals 3. At t equals 1, it looks like it's about, well, let's see. Let's call it t equals 2 here. It looks like it's moved over 1 light year to the left. Okay? And then at t equals 3, maybe it's moved over another light year, just roughly speaking. I didn't draw it exactly to scale there in terms of a certain slope and certain velocity therefore. But the key point here is it's an object moving to the left. It's clearly not going, it's clearly going less than the speed of light because the slope is greater than 1. Again, you'll never have, if this is a slope 1 and this is actually slope negative 1, you'll never have any slopes here that are less than 1. You'll also have slopes for world lines of objects that are greater than 1. And just by inspection, we can see, yes, that's greater than 1. It's going pretty fast, but not as fast as the speed of light. And it's moving in this direction, in the negative x direction. Key point here, though, that I want to point out is, look where these intersection points are. And essentially what this is saying is, this is an object that at x equals 0 starts out at 3 light years and then starts moving toward the left in the negative x direction. And if these green lines represent various things that at t equals 0 started off from the origin, in this case, all 3 of these started in the x direction. This one started in the negative x direction. When you have the intersection of 2 world lines, that means those 2 objects inhabit that space-time point at the same time. In other words, if we had shot a light beam off from the origin here at t equals 0, And at the same time, we had some object, spaceship say, that starts at the x equal 3 light year point and then starts moving essentially toward us along the x-axis. Somewhere in between, those two objects would meet. The spaceship would run into the beam of light. So the spaceship is coming this way, as the red line indicates. Our beam of light is going that way. And at a certain point, they would meet. This is the meeting point right here. It tells us what time those two objects met and at what x value in between there. Same thing, say, for this object here, v equals 0.5 c. That means we shoot it off from the origin at 0.5 c, heading in that direction. This object here, at t equals 0, started off heading towards us at a certain velocity. And the two objects met, if they're two spaceships, hopefully not head-on, but pass by each other right at this point here. Because that means they inhabited the same space-time point. They're at the same location at the same time. And again, hopefully on slightly different tracks there. And then similarly up here. So this object here, our third object, started off at a slower velocity, 0.33 c, not 0.5 c. So this object here will clearly catch the incoming spaceship first. We'll meet up with the incoming spaceship first. And then the second outgoing spaceship, say the one going 0.33 c, takes a little bit longer, but eventually they meet up as well. And you can see, again, the intersection points tell you that that's where the two objects met up, or where, in this case, the light beam and the object met up at a certain point x, wherever we are measuring along our lattice of clocks here, our measuring system, and then at a certain time t. So when we have multiple world lines on a diagram and they intersect each other, then we know those two objects essentially occupy the same point in space and time at that given instant. And if they're spaceships or something, they could even collide with each other in that case. I mean, technically they would collide with each other, but we'll assume maybe our measuring system isn't so fine that they couldn't just pass by each other very nicely, so we don't have any accidents and things like that. Okay, so a little bit more space-time diagrams. In the next video clip, we're going to look at different ways we can actually do some plotting and sort of strange ways to do it. It'll be very unusual. It'll seem strange, but we'll find later on that it'll make a lot of sense for us to do it this way.